control for a non-linear system. Okay, so a more generic system can be written as x dot equals fx comma u. Can f can have any form. It could be quadratic, you have sines, cosines, doesn't really matter. Okay, so the way we'll go about this is we will linearize this system about an operating point. And for this, let's just call that point x0, y0, x0, u0. And use the linearized system for control. Okay, what that would mean is if you have, let's say, a double pendulum and you're trying to get, or single pendulum is simpler. So single pendulum, and you're trying to make it upright about the vertical position, then that vertical position is going to be your operating position. So we know that we require that position is given by theta equals 0 and theta dot equals 0. And because the mass is just below the pin joint, you don't require any torque. So the u0 will be 0, x0 will be 0, comma 0, and that will be operating point. Okay, now for something else, like say, for example, if you want to hold it at a position which is at 30 degrees instead of 0 degrees, then your equilibrium position would be 30 degrees, which is 0.5 radians, comma 0 for velocity, and there's a non-zero torque involved for holding that position. So that x0 will not be 0, u0 will not be 0. You'll have to specify that appropriately. So once we have specified that operating point in terms of control and state, then we'll linearize the system. So what it means is we'll assume x as x plus delta x and u as u plus delta u. Where I'll explicitly put the operating point there for x. And then we'll pass this through the equation. So putting in 1, we have x dot plus delta x dot equals f of x plus, so x0 dot plus delta x u0 plus delta u. Okay, now what we can do with the f is that we'll use the Taylor series approximation to expand that about the operating point x0, u0 plus df dx, x minus x0 plus df du, u minus u0 plus higher order terms. So those would be typically d square f dx square and d square f du square, but you will also have x minus delta x square, x u minus delta u square. So this is using Taylor series. You can refer to the internet for what's a Taylor series approximation. It's basically this. Okay, but we know that at equilibrium, x dot 0 is f of x0 u0. And that is the state is accounted for in the differential equation. So we can cancel the things from the left-hand side with the right-hand side, and we are left with this equation. delta x dot equals tf tx. Okay, now x minus x0 is delta x, and tf tu times delta u. Okay, the reason I wrote this like this is because we will now define our A matrix as df dx and B matrix as df du. Okay, and then we can proceed with our controller development, where A is blend both these equations, where A is df dx, B is df du. So pretty much once you have the form for that differential equation, x dot equals fx comma u, you pretty much use this trick to linearize the system. And once you have the linear system, you'll develop a controller based on the linearized system. Now, one thing you want to remember, however, is that so this, we'll take this, use LQR or pole placement to compute delta u. Now will be a function of delta x, right? So the system is set up. And once you do that, note that the control is u equals u0 plus delta u. So do not forget to put the u0 in your control system. It is u0 plus delta u, and the delta u comes from LQR or pole placement. So most times when you linearize, say, a pendulum about upright position, u0 is 0. So that system is actually linearized. Well, it's not linearized, but it's already at the operating point, so it's easier to do the linearization. But for something else, more complex things like there is no equilibrium position like that of a pendulum, you might have to figure out what u0 is. Okay, so let's see how to apply this. So we'll see an example we've seen before. We've talked about differential drive car. In which the equations were x dot equals v cosine theta, y dot equals v sine theta, and theta dot was omega. So if we assume that x, so I'll distinguish from my small x, the way I write it down. Let's say that the state x is x, y, theta. My controls, which sit in U, are v and omega. Right? You can control the speed, linear speed. You can also control the angular speed by changing the speeds of the motors. So we'll assume an operating point. So x0 and u0. So that would be small x0, y0, theta 0. And for u0, it will be v0, omega 0. Okay, so let's assume that we know that. I'll tell you a little bit more background about how to compute that a little bit later. And let's just linearize the system. So what we need to do is we'll identify what small f is. And once we have small f, we can compute the linearization. Okay, so we have dx dot equals a dx plus b du. So here f is going to be v cosine theta, v sine theta, and omega. And remember that x is x, y, theta. Okay, so let's now start computing the linearization. A is df dx. So this is how you will do it. The first row of f is v cosine theta. So you'll take the derivative of v cosine theta with respect to x. So let me just write it down. Then you'll do the same derivative with respect to y and same with respect to theta. Okay, and then you take the second row and do the same thing. Dx, dy, d theta. Okay, so now we can write it down much easily now that we've wrote down the expression. So the first term, the derivative of v cosine theta with respect to x is simply 0. Second one is 0. Third one is, so derivative of cosine is negative sine. So negative v sine theta. And we have 0, 0. And then derivative of sine is cosine. And then we have 0, 0, 0. Okay, so that's the A matrix. It has one row which is entirely consists of zeros. Okay, B is going to be a new page. df du. So this is how we go. So remember that u is v and omega. So we need to take care of both of this. So d v cosine theta dv, d v cosine theta d omega. The second row of f was sine theta. So dv sine theta dv, dv sine theta d omega. The third row was omega, so d omega dv, d omega d omega. Okay, so the first column is going to be just cosine theta. 0, sine theta, 0, 0, 1. So we have dx dot equals 0, 0, 0, 0, 0. Minus, so remember that this is about an operating point, and we said operating point was x0, u0, and I just put some zeros there. So v0, sine theta 0, v0, cosine theta 0, 0, delta x plus cosine theta 0, sine theta 0, delta u. So note that again, the control. So once you have ax plus b, you can compute delta x using linear quadratic regulator or pole placement, but your control should be u plus delta u. Now, this is pole placement LQR, and this, the question is, how will this come for a car? Now, for a pendulum, we know that we want to operate about the vertical position, so that's 0. But for a car, we want the car to drive around. So what you will do typically is, first you will, let's say that we want to solve the problem of a car going on a trajectory. Now, we had a different method of doing that, and I'll come to that method in a bit. What you would do is perhaps use trajectory optimization to solve for u0 as a function of time, such that it will go along that path. That path could be a Leibniz state, circle, whatever you want. So that will be u0. It will tell you what you need to do if the world was perfect and you are able to follow something perfectly. But in the real world, your sensors are not perfect. The world is not perfect. And so when you try to follow the path, you will deviate from the path. And that delta U will actually help to put you back on the path. So this will come using trajectory optimization. And this is usually open loop, which means the function of either time or something else, but not of state. And this is the part which is closes the loop, which uses feedback. So what I meant is, let's say this is the path. U0 of t, which is open loop, keeps you on the path. But the moment you deviate from this path, then delta U will push you back to the path. So because delta U is based on k delta x, and this is giving you the error in tracking. So the difference between a car example and the single or the double pendulum is that in single pendulum, we are doing what is known as a set point control. We are controlling a particular position. And for a car, we are doing trajectory tracking. So if you go back and see the class where we talked about feedback linearization, we had two problems. We had control of the double pendulum about the vertical position, but we also had this problem where we are trying to swing the double pendulum about a trajectory, or make the double pendulum track some curve on 2D space. That is also a tracking control problem. Okay, so this is different from what we did for the car originally. So if you recap, so this controller is different from what we did previously. So what did we do previously? Well, we wrote down the equation of a car, and then we said the controller is x dot equals x dot ref plus kp x ref minus x. Controller for car. And if you remember, this is actually the same as feedback linearization. This is exactly what we did for the double pendulum. We can actually show that this sort of does what it's supposed to do, and it tracks x ref by doing the simple transformation. We can move this the things on the right side to the left side. So we have x dot minus x dot ref equals kp x ref minus x. And so if this is some kind of an error, right, then we can write this will be minus error. So we write it as E dot. So E dot equals E dot plus KPE equals 0, right, because it's minus E. And then if you don't know, this is actually something which will asymptotically go to 0. So if you try to plot E as a function of time, you see that it will actually go down to 0. This will be E0. It's exponentially go to 0. Okay, in other words, if you solve for E, it's going to be something like A times E raised to, I have a problem here. I should not have used E. Let's define this differently because E is what I need to use in the solution. It's called as epsilon. Okay, so the reason I use epsilon is because the solution to this is actually exponential Kp times T. So this is a solution. So you can see that as T goes to infinity, the epsilon goes to 0, and that's what we see here. I've shown here. Okay, so this controller which we had was driving system exponentially to 0, and this comes from feedback linearization. You can check this form with the form we had for the double pendulum, and note that this is very different from the controller we have here in case of the LQR. We have to do an optimization to figure out the open loop and then do feedback control. So, any questions on this? Okay, we've seen the equation of a manipulator. This is how we want it to be written. So let's just first write it down as what we've seen before. So M of Q, Q double dot plus C Q, Q dot times Q dot plus G of Q, gravity torque equals P of Q U. Okay, the reason I wrote P of Q U, which might be different from what I've written so far, is that the system we'll see here will be such that they will be underactuated, which means that there won't be the same number of actuators as the number of degrees of freedom. So example would be, let's say, a double pendulum. You have 2 degrees of freedom. So in the past, you've looked at 2 degrees of freedom, 2 motors. But we look at systems where there's only 1 motor. And this is a more generic way of writing these equations. This will always be the number of actuators. It will always be M cross 1. And then B of Q will be N cross M. It'll basically map out the actuators to the degrees of freedom space appropriately by choosing B of Q. Normally, B is a constant, is not a function of Q, right? The torques on the actuator are just the way it is, tau 1, tau 2, and so on. But I'm writing it as B of Q because after this, we'll see a bicopter, a quadcopter in 2D space, which has only 2 motors. In that case, we'll see that you will have B would be a function of Q, B function of state. In fact, this is an example. The differential wheel is actually an example of a system which has that dependence. If you look at, if you look at this system, you see this F. You can see that it can be written as B of Q times U. Where U is U, V and W. So this is a different B, not the same as this B. B of Q, in fact, Q is theta, and then V and W. Okay, so that's another example where it's not a function of, it's not a constant. Okay, so we have the system and we are supposed to linearize the system. So remember what we did. We need to write the equation in this form: x dot equals x comma u. So what we'll do is we'll assume that x is q dot. So this is the angular velocity. So let's write this down. So we want x dot, which will be q dot, q double dot equals, we'll keep the q dot as it is, but to get q double dot, which we see is here, what we need to do is we need to move c and g to the other side, and then we need to invert n. So we'll do that. G of q minus c q dot, what should be minus plus p of q. So this is our f of x. So now we have the equation in the form we would like to be in. Now let's think of linearizing the system. Again, when you're linearizing it, this is about some operating point. So you've got to assume that there's some x0, u0, which you've already thought about. And then you linearize about that. This is f1, f2. Yeah, I wrote it down because it will simplify. We can do it step by step instead of trying to just writing down final values. So we need to compute A and B. Now what I'm going to do is I'm going to write that A as A tilde, and just because A is not the problem is going to be B. I already assumed a B to be in here. And so if I use another B, then it's going to interfere with that B, which I defined. So I'm going to call that B tilde, that's a linearization. So A tilde will be df du, df dx, and B tilde is df du. Okay, so that again, B is because I don't want to step on the other B, which has already been defined. Okay, note that F is F1, F2, where F1 is Q dot, F2 is M inverse Q minus CQ, Q dot minus GQ plus P of Q times U. Okay, so let's compute A. So again, you do the same thing, which is you differentiate. I forgot to put one more thing. X is Q and Q dot, right? I need that. So D F df dx is going to be, okay, so the same way as I done previously, you have two variables Q and Q dot. I need to take derivative of F1, F2 with respect to those. So df1 dq, df1 dq dot, df2 dq, df2 dq dot. Okay, now let's look at what F1 is. F1 is Q dot. Okay, now Q dot is not one value, but it is all the states. So if you have like a 5-link pendulum, then it will be those 5 Qs or 5 angles. So df1 dq, we take the derivative of Q dot, which is in F1, with respect to Q, you will get 0. Let me actually just write this down. This might be the best way to explain it is to just write it on D. So df q dot dq, dq dot dq dot. Then we have d of dq m inverse q minus c q q dot. There's a lot of space. Just put it down this way and then I'll simplify it later. Okay, so let's look at the first two terms in the first row. It's clear that this is 0, right? Now this term, it looks like 1, but it's actually not 1, it's I, because Q, remember, is the dimensions of the giant angle. So if, for example, you will have Q1 dot, Q2 dot, Q3 dot, Q4 dot. When you take the derivative with respect to Q1 dot, Q2 dot, it will basically give you an identity matrix. So this is going to be the identity, not 1, just because you have, it's not one dimensional, it's n dimensional. Okay, let's simplify the other part, which is df to dq. So this is going to be d of dq. Just do it on the new page. Okay, so let's do that derivative. Now you see that there is m inverse and there is that other term. I'm just going to use chain rule. Okay, and then keep the second term as it is. And then keep the first term as it is, take the derivative of the second one. So we have dc dq dot. Okay, that first term in there is actually it's a big mess because the mass matrix is usually nice in terms of how it looks because there's like cosines and sines. But the moment you take an inverse, you remember in the inverse, you take 1 over the determinant of something, that has cosines and sines. And when you take a derivative of something which is 1 divided by cosine, just it's a whole big mess. So what people do is they don't really take the derivative of m inverse with respect to q because it's not computationally very efficient. Instead, what they do is they do the following trick. They write m, we know that m inverse is I. Okay? If you multiply something with inverse I, then we take the derivative. If we take the derivative of both sides with respect to any variable, let's call that, let's say q for that matter, dm dq, m inverse plus, and then we know that the derivative of identity is 0. So now we can move things around. Okay. And now what we'll do is we'll pre-multiply with m inverse. So we have m inverse m dm inverse dq equals. This is identity. And so we have computed EQ. Okay, so what we have been able to do is we've been able to replace dm inverse dq with dm dq, which is somewhat less computationally intensive as dm inverse dq. But here's the issue, which is M is a matrix. So usually what we have done so far is we have taken df dq, for example. F is a vector, and then we take a derivative of vector with respect to a vector, you get a Jacobian. When you take the derivative of a matrix with respect to a vector, you get a tensor, which will have 3 dimensions, not 2. Jacobian, remember, has 2 dimensions. When you take derivative of vector to vector, you get Jacobian, which is 2 dimensions. This is going to be matrix 2 by 2 or 3 by 3. Derivative with respect to will be a tensor 3 by 3, and then so then the calculations are pretty more complicated than what you see. So this is what you will do normally. That is, you will find a way to compute that. It so turns out that for the problems we'll consider in this class, where we'll typically talk about things which are in which acceleration in the nominal state is 0. So for example, if you keep a pendulum upright, the acceleration of all the joints in the nominal operating point is 0. The Q, this is, remember, at the operating point, so it will be Q double dot. Now this is equal to 0 at the operating point. So as long as you are at the operating point, this is actually M Q double dot, right? As long as you're at the operating point and the operating point is acceleration is 0, that term will reduce to 0, and you don't have to worry about taking the derivative of M inverse with respect to Q. Okay, so we will not look at cases where we don't have that condition in this course, and so we do not have to worry about dm inverse to Q. If you have a problem, however, like for example, a quadcopter which is spinning fast and its acceleration is changing at the operating point, then you cannot take that equal to 0, and then you'll have to deal with that. Perhaps you can just assume it to be 0 and use an incorrect linearization. It will still work, but it's not guaranteed. So I'm going to make a note of that. These things, so this one is 0 because G is a function of Q. There's a mistake here. This should be a function. My bad. This should be Q. This should be Q. So this one is not this is not equal to 0 because G is a function of Q. Gravity torque is a function of Q. So that's not 0. And then this one will also not be 0. This term is normally not 0, but everything we are doing in this course, we will ensure that at the operating point, we'll see that we are dealing with situations where Q dot is 0. And so since the nominal speed is 0, that term drops out. Okay, so what we are left for df df2 dq is M inverse Q times minus dg dq. And then the term involving B looks something like this. I should write it this way. This will be M inverse P J D Q U J, and you just sum over J. So what this literally means is that you first take the product of B times U and then do the derivative with respect to Q. Okay. Okay, so we're not done yet. We still have the last term, which is dF2 with respect to dQ dot. Go back. We figured out this term. We are still left with this term, so we'll do that less. dF2 dQ dot is going to be M inverse P dQ minus G of Q minus C Q dot plus P of Q. Okay, so the good thing about this expression is that this is a function of Q, so you don't really take this derivative will be 0. This is not a function of Q dot, so it's derivative is 0. We know that this is 0 at the operating points, that drops out, and then B of Q is not a function of Q dot. So this entire thing is 0. Okay, so to summarize, our A matrix is a lot more complicated than what we started with. It's going to be A tilde is dF dQ, dF dx equals 0 I M inverse, so minus M inverse dG dQ minus, plus M inverse D. Summation M inverse dB dQ ju j, and the summation is over indices j, and then I and 0. Okay, so we're done with A. Now let's get B. P tilde is dF du. Okay, what was F? F was Q dot M inverse Q minus C minus G minus C Q dot minus G of Q plus P of Q U. Okay, so from this, you can see that P tilde would be dF du, which is you need to take the derivative of Q dot with respect to U, and that's clearly 0. So the first rows will be 0. And then we need to take the derivative of this expression with respect to U, and we see that this term would be 0. This term would be 0 because it's not a function of U. The only term which will be a function of U is this one. And so the derivative of PQ with respect to U, BQU with respect to U is going to be just BQ. So you're left with 0 and M inverse Q times PQ. This is B. This is A. Okay, so you see that it's not very straightforward to do, and the whole thing is complicated because of that mass matrix which sits in front of Q double. That's why we have these complications in computing the linearization. Okay, so let's see how to apply this. Now, this is what the example we'll look at. Okay, it's a double. So underactuated. Double pendulum. So what does that mean? Well, here is pendulum. I've drawn two because we can get two cases. Okay, so one way we can get an underactuated pendulum is we actuate this link. There's a torque or a motor at first link, and it can provide a torque U1. You could also have a torque at the second link. So note that those torques don't appear on both links. There's only one torque. This one is known as a Pendubot. And this one is known as a acro. So why acrobat is because when acrobat swings on a pole, he or she is using the muscles on his hip to move. You cannot apply a torque with your hands. You can only apply it with your hips. So that simulates a person on a swinging bar. And that one is called a Pendubot. Okay, so here we have Q1 and Q2. So degrees of freedom equals to Q1, Q2. Actuators equals 1, U1 for Pendubot, U2 for Acrobot. Okay, so why is it complicated? Well, now the question is, you're trying to stabilize the system about the vertical position. And then the question is, how will you do this? Well, UI equals minus K1 Q1 minus K2 Q2 minus K3 Q1 dot minus K4 Q. So this is an example of a feedback controller because it uses the information from the sensors Q1 and Q2. Now, if I give you such a system and ask you choose K1, K2, K3, K4, and that is really hard because you have no idea how you can tune them because there's only one actuator. When we had two actuators, sort of easy. We could just, if there was two actuators on both links, you can put a PD controller, let's say for this link, the shoulder joint, you just use the information from the forearm to control that and use the sensor information from the elbow joint and angular rate to control that one. So two actuators is easy, but one actuator is really hard. How do you choose those gains? It turns out that what you can do here is you can linearize the system, just like I did it in the equations, and then use an LQR controller to control the system. And the gains which come out are very non-intuitive. You have no idea why those gains came, except for saying that there's this calculation which goes. It's kind of sort of like magic that that thing works. And if you look at videos online, you'll see people doing it. They probably use some manifestation of pole placement or LQR. LQR is more popular. Okay, so this is pretty much copy pasting the code I wrote down a long time back to simulate a double link pendulum. So I have code which basically does the derivation of equations. All these things are new or not new, they're all old. But the additional thing I did was after I finished printing CJ, all that, I have some code which will now compute those the linearization matrices. I have some additional things. You don't really need DG, DQ. The only thing you need is, you need DG, DQ. You don't need DG, DQ dot, and these things are not needed. But anyway, I wrote them down so that way you can get them. And once you get them, you just put it in that same form I wrote down in my notes. Okay, so run this first. Okay, and so it gives all these things which was there before, but the extra thing is these things. So you can see that DG, DQ is not 0, but all the other terms are actually 0. DC, DQ is not 0. Okay. Now, let me open my simulation. It's open. Okay, let's first play it. Okay, so there's nothing interesting going on here because it did its job. LQR is working as expected. It's just keeping it stable now. You have to convince you that something like this is actually stable, what I need, so it's all 0. I need to actually perturb the system because in the perfect world, in simulation, it can just stay there upright without any torque. So what I'm going to do is I'm going to add some disturbance to it. And that's where you see the controller works. That's my controller. It's a LQR, but the K comes from using LQR gains. And I'll show you what the code, what things I copy pasted. But what I'm going to do is let me add a disturbance, not disturbance, but sensor noise. So what this is doing is going to do is it's going to add noise to the velocity of link 1 and velocity of link 2, and the disturbance is 0.05. So any point of time, you will have a deviation of 0.5, and it's a normal distribution. So depending on what it picks from the normal distribution, that's what it will use. Okay, so now you can see that it's actually doing something which is balancing it. So that it stopped because I stopped the animation there. But this is what the code looks like. And then you can also, I don't know how well this will work, but this thing introduces a deviation at the top. So it produces a disturbing top. And that's maybe quite high. I don't know. Let's see if it works. It might actually fail. Yeah, so it failed because remember that my controller is valid for small perturbations about 0. So if you are going to perturb it too much, then it's going to fail. Now, it might actually work if I reduce this to 0. I think it failed here too. Yeah, that's way too much, just out of his league. I think it failed here too. Yeah. Okay, that's a little too much. I should have checked this before I even try to do it. Okay, so a little bit about the code. Remember that there were 2 systems I could do. I could do a Pendubot or an Acrobot. The Pendubot has B10. It's just this B basically tells you which actuator, where is the actuator placed. Here it's placed on link 1. If you uncomment this and comment this out, it will basically be an Acrobot. And so you can simulate both systems using this. The second thing I want to say is that besides copy pasting the code from previous time, I also added these. You can see these. I have a function called linearization, which computes A, B. Okay, so this is the A tilde I wrote down there. I have 0, 0, and then identity. Then I have M inverse times DG, DQ, and then this term is actually 0, so you can just ignore that. And then B is 0, inverse M times B. And then this just returns the A and B matrices. And then I would have somewhere, let me see where do I do it. Okay, so I get the A and B. I initialize my Q, R, and then I used LQR to compute the gain K. You can also use this function, which I found somebody had coded a LQR without using the controls library. You can use that too. Okay, so what's interesting is that if you make it print, okay, I want to stop the program, so I just put some random thing which will stop it. Okay, so that's, ignore that error, but this is the gain. I would say that's very non-intuitive. I have no idea why this is 168, 162. Why is this 72? Why is this 42? Why is it shouldn't be the same? It's like no idea why that's true, but that's what comes from theory and it works. If you decrease this to -4, it will be more aggressive. Those gains will increase probably by a factor of 100 because I decreased it by a factor of 100. You can see 1421, 1294, 600. Okay, what else? That's pretty much it in the sense that I just, okay, only one more thing which I might want to add is that I just call that, I have a function called controller, which picks up the K and then does U minus K times Z is the state. And then that has to be called in my equations of motion, which are my right-hand side, which is here somewhere here. Okay. It's called here and then it goes in B times